Okay, so remember we are working on the problem. The t derivative of u is equal to the double x derivative of u. We have some boundary conditions. We know that u of 0t is equal to u of 1t, and that's equal to 0 for all values of t. We might want to say all positive values of t. And then we have an initial condition, u of x is 0 is equal to f of x. So we're imagining a rod, for example, going from point 0 to point 1. The boundary conditions say that the endpoints, the end of the rods, are going to be kept at a 0 temperature. And we saw in the last video that if, okay, this is a big if, we saw if f of x is equal to the sum k equals 1 to n bk sine k pi x. So if, again, big if, f is equal to a linear combination of the sine functions, then u of xt defined by the sum k equals 1 to n bk e to the minus k pi squared t sine of k pi x solves this problem. Okay, why does it solve the problem? Well, we picked these two functions using that method of separation of variables. We picked these two functions explicitly so that they would satisfy the PDE and the boundary conditions. And then, well, if f of x is equal to this, if you plug in t is equal to 0, then you just get bk sine of k pi x, which is f of x. Okay, and the fact that this satisfies the PDE is the fact that this is a linear equation is critical to the fact that this equation satisfies the PDE, and the fact that these boundary conditions are 0 is critical to the fact that this satisfies the boundary conditions. Like if there was a 1 there, and so that these functions were equal to 1, well, when you added them up at the endpoints, you wouldn't get 0, you would get n. So the fact that the PDE is linear, the boundary conditions are homogeneous, meaning 0 means that this is going to satisfy the since each term satisfies the PDE and the boundary conditions, any finite sum of them will as well. And any infinite sum will as well, we just have to worry about convergence. Okay, now very often, in fact, I don't know, most of the time, when we have an initial condition like this, we're not given it as a linear combination, we're given it as some formula. And so the question that I want to ask is, can we come up with a formula for the bk's in terms of f of x? Now, just looking forward, where we're going to be going with this is that we're eventually going to replace n with infinity. In the case that we replace n with infinity, we have a series here, and every function, more or less, can be written as a series of the sine functions. There's a huge caveat there, but we haven't got to that. We'll get to that later. Okay, but essentially every function can be written as a series, and so this computation that I'm about to give you for the formula for bk is also going to work for the case that we have an infinity there rather than an n, but we'll get to that later. For now, assume f of x is equal to this. Can we get a formula for the bk's in terms of f? The answer is yes. There's a very, very easy formula. So the integral 2 times the integral from 0 to 1 of sine of k pi x times sine of L pi x, like this. So here k and L are integers. 2 times the integral from 0 to 1 of sine k pi x times sine L pi x. There should be a dx here, I guess. This is equal to 0 if k is not equal to L, and it's equal to 1 if k is equal to L. So it's equal to 0 if k is not equal to L, and it's equal to 1 if k is equal to L. So you remember from your linear algebra class that we can define an inner product, which is a generalization of the dot product in Euclidean spaces. Here it's going to be equal to 2 times the integral from 0 to 1 f of x g of x dx. And so this right here is just the inner product of the sine functions. So what does it mean when the inner product of two functions, or in general two vectors, are equal to 0? It means they're orthogonal. So what this means is that the sequence of sine functions, sine of k pi x, this is orthogonal. And actually, relative to this inner product, they are orthonormal, meaning that their norm is equal to 1. Sine squared, if you do the integral of sine squared k pi x, that's going to be equal to 1 by this formula here. And as long as you have the 2 on the outside. Okay, so given this, we can compute what the BKs are in terms of f. And you might remember this from linear algebra. So again, assume that f of x can be written as a linear combination of the sine functions like this. If I do 2 times the integral from 0 to 1 of f of x times sine of L pi x dx, well, I can just replace f of x with this sum here. So this is 2 times the integral from 0 to 1. We're looking at the sum k equals 1 to n bk sine of k pi x times sine of L pi x dx. Now, this is a finite sum, so there's absolutely no ambiguity in interchanging the integral and the sum. So this is going to be the sum k equals 1 to n bk 2 times the integral from 0 to 1 sine k pi x sine L pi x dx. Well, this is great news for us, because I know this integral here is equal to 0 if k isn't equal to L, and it's equal to 1 if k is equal to L. So L is fixed, and we're summing over k. So the only term in this sum that's not equal to 0 is a sum corresponding to L, assuming L is less than n. If L is bigger than n, they're all equal to 0. But if L is less than n, the only term in this sum that is not equal to 0 is a sum corresponding to k is equal to L, in which case we have BL, and then this integral is equal to 1. So in other words, it says BL is equal to 2 times f of x times the sine of L pi x. In other words, it's just equal to the inner product of f and the sine function, which, if you remember from your linear algebra class, that's exactly what we get when we have an orthonormal sequence. And the sine functions are an orthonormal sequence here. Okay, well, fine. This is great for the rare case when f of x just happens to be a linear combination of sine functions. And if f of x is not, any function that you can think of that's not just thinking of a linear combination of sine functions is not going to be a linear combination of sine functions, right? If you just think of like cosine. Cosine. Cosine is not a linear combination of these sine functions. If you think x squared, that's not a linear combination of these sine functions. Okay, so if you just think of a function that doesn't happen to already be explicitly a linear combination of these particular sine functions, then f of x is not going to be a linear combination of sine functions. Okay, so the backup question that we're going to ask is, okay, how well can we approximate f as a linear combination of sine functions? And not just sine functions, these sine k pi x functions. Okay, so how well can we approximate f as a linear combination of these sine k pi x functions? Okay, so in other words, what if we know that f of x is approximately equal to this sum bk sine k by x. So what if we know f of x is approximately equal to that? Question one is, if it's approximately equal, what are the bk's? Like, what bk's give me the best approximation? Okay, because now if f of x is equal to x squared, I don't know what the bk's are, right? So the first question is, what bk's are going to give me the best approximation? Okay, so assuming that we figure that out, that's what we're going to do in the next part of this video. Assuming that we figured that out, then this function here is still going to satisfy the PDE and the boundary conditions, and is going to satisfy the initial condition to the extent that f of x is approximated by these functions here, by the sine functions. Okay, it now becomes a question of how well does our approximation need to be for whatever we're doing. Okay, and as we will see, essentially any function can be approximated to an arbitrary precision by a linear combination of sine functions. So then for a given f of x, we just figure out how many terms we need to take here, and then we'll get our approximate solution, and it'll be within whatever precision we have decided. Okay, as long as we take n big enough. But the exact mechanics of that we're going to get to later. The question that I want to answer now, so the answer to this question is arbitrarily well, as long as we take n big enough. But the next question is, okay, well, I know that if f is literally equal to this, then I should take bk equal to the integral of f with the bk, integral of f with the sine functions. Okay, so if f is literally equal to that, then I should just take bk to be the inner product of f and sine k by x, where the inner product is defined like this. Okay, but the question is, what if f is not literally a linear combination? What are the bk's going to be? And it turns out the bk's are going to be the same exact thing. So let me explain why that is now. Okay, and this is also going to explain what one of the ways in which f of x can be arbitrarily can be approximated to an arbitrary precision with these linear combination of sine functions. Okay, so theorem. The choice of coefficients bk, k equals 1 to n, that minimizes the integral from 0 to 1 of f of x minus the sum k equals 1 to n bk sine k pi x squared dx. Okay, so what are we doing? F of x minus this, we're squaring it and integrating it. There should be a 2 here, just to keep things consistent with what we're going to do. So the choice of bk's that minimizes this expression here. Okay, so this is called the L2 norm, or the square of the L2 norm of f minus these functions here. It's positive, so the smaller this is, the closer f and the linear combination are to each other. If these are equal to each other for every x, the integral is going to be equal to 0. The smaller this integral is, the closer f and these are to each other. Okay, and by close, this is how I'm measuring closeness, right? This is just a generalization of the magnitude of a vector in Euclidean space. Okay, the choice of bk that minimizes this is bk is equal to 2 times integral from 0 to 1 f of x sine k pi x dx. Okay, so I want to prove why this is true. Now to do that, I'm going to use the following notation. I've mentioned it over there before. So the inner product of two functions, f and g, is going to be the integral, 2 times integral from 0 to 1 of f of x, g of x, dx. Okay, and so the norm of a function squared is just going to be the inner product of f with f. Okay, this is familiar from your linear algebra class, and this is also the dot product. Think about it in vectors, just regular Euclidean linear algebra. The dot product of a vector with itself is its magnitude squared. I'm also going to use the following. I'm going to say that phi sub k of x is equal to sine of k pi x. Now, if you looked at the way I've done this in the notes, it's all very explicit. With integrals and things, you can read it there. But I'm going to do it differently in this sort of more abstract formulation with inner products in these phi k's here. The reason I'm doing that is because I want you to see both of them. Both are important. In terms of explaining things on the board in space, using this notation is going to be easier. And the reason that it's easier, so here's how I like to do it. In addition to the notation being easier, this is one of those topics where if you just make things a little more abstract, the computations get much easier to do. Sometimes if you make things more abstract, the computations get difficult because things aren't as explicit. But here, I think if you make the computations a little less or a little more abstract, they get a little less tedious. Okay, and I don't know. Maybe I'm wrong. Maybe you disagree. Compare what I do here to what I have in the notes. You tell me what you like. Okay, so here's what we're going to do. I want to compute this. This is just the inner product of f minus the sum k equals 1 to n bk phi k with itself. So it's going to be this times f minus. Okay, and now since I have two different sums, I'm going to use a different index variable. I'm going to use L equals 1 to n here. PL phi k. Okay, and notice another good thing about this is that the argument goes away. There's no x's. In addition to just not wanting to have to write the x's over and over again, this is something, there's a subtlety here that we're not really dealing, when we're dealing with like the, using an integral to measure how big something is or how close two things are, we don't really care about what's happening at each point. We care about what's happening over the whole interval. And so that's why that's why I prefer to write it without the argument. It sort of emphasizes that. Okay, now this is just, if you just kind of expand this out, it's just basically kind of like an inner product version of foiling, for example. This is going to give you the inner product of f with itself plus the inner product of that and that. So it's going to be plus the inner product of bk. The sum. I'm going to stay in here and then move out of the way. The sum k equals 1 to n bk phi k. The sum L equals 1 to n bl. Sorry, I had a k there. There should be L bl phi l, like that. And then the mixed term, so it's going to be that, the inner product of that with that, minus the inner product of that with that. And for that, maybe think about why this is true. This is minus 2 times the inner product k equals 1 to n bk phi k. Okay, so really it should be, forget it. It should be minus the inner product of f with the k sum, and then minus the inner product of the L sum with f. But the L, if you do the inner product of the L sum with f, that's equal to f with the L sum, which is equal to f with the k sum. Okay, so if that last part was a little bit confusing there, just well, you should be writing down and following along in general. But maybe this last step is the most confusing of all of them, but just, think through why that's true. Okay. So now over here, I'm not going to copy everything else down, but over here I can pull both of these sums out. And when I do that, this is what I'm going to get. I'm going to have a double sum. On the outers, I'm going to have k equals 1 to n. The inner sum is going to be L equals 1 to n. And then we're going to have bk, bl, vk, vl. So again, I did several steps there. Make sure you can follow them. Okay, now what's happening here? Well, on the outer sum, I have a k, and on the inner sum, I have l. So for each term on the outer sum, k equals 1 to n, imagine fixing k. What do I have going on the inner sum? Well, L is only going to, again, for a fixed k on the outer sum, the only time I'm going to get a non-zero number here is when L is equal to k. So then what I get is going to be bk squared times the inner product of phi k with itself. But what is that? It's 2 times phi k squared. Well, that's 2 times the integral from 0 to 1 of sine squared k pi x. We saw before that's equal to 1. So this is equal to 1. Okay, this is going to be minus this. So it's going to be minus 2f times the sum k equals 1 to n bk vk, like this. Okay, well now what we can do, I can pull this sum out over here. So I can pull this sum out, and I'm going to get minus the sum k equals 1 to n 2 bk f vk, like this. And then now I can just combine this into one sum. So I have something like this. Now, what I'm going to do, I just want to point out one thing. We now want to find the bk's and minimize this. If you think about this as just kind of a multivariable minimization problem, and you take the derivative of this, if you take the derivative of each term with respect to bk, what you get is 2 bk minus 2 the inner product of f with vk. And if this is equal to 0, it says that bk has to be equal to the inner product of f with vk. That is this right here, right? This, using that notation over there, is the inner product of f with vk. So I know just by kind of basic multivariable calculus, first level, if there is going to be a minimum, if there are a set of bk's that minimize this, it's going to be given by this formula here. Okay, and so then you would next have to somehow make an argument for why there are going to be a set of bk's that minimize this. Maybe there's not a set of bk's that minimize this, but you have to make that argument. Another thing that you could do, excuse me. Another thing that you could do is show that, again, you gotta have to somehow show there's a minimum. One way to show there's a minimum would be to show this is a convex function, which is essentially what I'm about to do. Okay, so that was a little side comment there. Okay, so what I want to do is right here, I'm going to complete the square here. So if I complete the square here, okay, by completing the square, I'm going to show this is a convex function. In other words, it's a function that looks like this. Like, it's going to have the same shape, basic shape as a paraboloid. In fact, it will be a multivariable paraboloid. Okay, in which case, if you have a paraboloid, you know that when the gradient is equal to 0, you're going to be at the minimum. All right, so I didn't mean to explain all of that, but it just came out. So this is going to be bk minus the inner product of f with phi k squared, and then we're going to subtract off this, so then it's going to be minus. That's just the completing the square thing. So what I can do is I can replace what I have in parentheses with this expression. I'm just going to write it a little bit differently. So we're going to have this. We're going to have bk minus the inner product of f with phi k squared, and then I'm going to have another sum. I'm going to separate this off. The sum k equals 1 to n f phi k squared, like this. Okay. Well, so what do we have going on here? Remember, my goal is to find the bk's that minimize this sum. The phi k, or I want to find the bk's, not the phi k's. I want to find the bk's that minimize this sum. I want to find those guys that make this sum the smallest. Now f is given, so we can't change f. The phi k's are given, we can't change that. The only thing we have any control of in terms of what choices we can make is going to be this middle sum. And now this sum is a sum of squares. So the way to make this the smallest is to make each of these equal to 0. See, if I had a mix of positive and negative things here, it would not. If this sum was a combination of positive and negative terms, then it would not be the minimal choice to make all of these equal to 0. Okay, but since I'm adding up a sum of non-negative things, if I want to make this the smallest possible, I want to make each term 0. Okay, so it's a very basic fact. If you're adding up non-negative things, if you know all of the terms in the sum are non-negative, the smallest that sum can be is 0. So we have a non-negative sum, the smallest it can be is 0, and that's going to be if bk is equal to the inner product of f and phi k. Now, this is a very general fact. It is a very widely used fact. All we have done here is just found the least squared solution for this function right here. Least squared and orthogonality, hugely important in, I don't know, any sort of area of analysis or anything like that. Incredibly important. This is just one use of it. And the other thing that I want to point out here, another good thing about the abstraction, instead of using the integrals, is that there's nothing that we used here that relied on the fact that we're thinking about integrals. What we just showed works for any inner product space. It shows, and it is a proof showing that if we want to minimize this expression right here, where the phi k are orthonormal, bk needs to be the inner product of f with phi k. Very, very useful fact, and here's a very generic proof. For our context here, the inner product is the integral of f with the sine kx functions. Okay, so again, what we have proven is that if f is a linear combination of sine functions, this is the expression for the coefficients. And the backup plan is if f can only be approximated by sine functions, these coefficients give us, the coefficients that find this way give us the best approximation, where best approximation is measured in this integral sense right here. Okay, that is it for this video. There's a lot of sort of manipulations going on here. Please make sure you understand all of those, because we're going to be doing these same manipulations that we did in the previous video and in this video. We're going to be doing those over and over and over again for the method of separation of variables, and I'm not going to explain them in much detail at all once we start looking at these.